In this video, we're going to take a look at section 8.2. Coming out of section 8.1, we learned about confidence intervals. We talked about point estimation, as point estimate being a single value for estimating the population mean. And we did mention that X bar is a point estimate of population mean mu. And we looked at an example of a confidence interval, 95.44 confidence interval for the mean. In section 8.2, we're actually going to look at a formula which establishes the confidence interval for one population mean mu. Now, the assumption in this section is that sigma is known. Sigma being the population standard deviation is known, which may be an unrealistic assumption, because usually if you know sigma, you should know mu, because the formula which defines sigma uses mu. You can go back to chapter 3 and look at the formula that we have for population mean sigma. We're looking at this expression on top. It uses mu in it. But nevertheless, that's the assumption in this section. The other assumption that we have is that our random variable x follows this symbol that you see. They call it a tilde. This one means follows. So random variable x follows n for normal with the parameters mean and deviation sigma. So we're assuming sigma is known, but we don't know mu. Remember, we never know mu. So that's the assumption, that this follows normal, or remember, central limit theorem required the sample size to be large. And sample size n is large if it's at least 30. So it's one or the other assumption. And it could be any sample, as long as it's greater than 30, the population that you sample from doesn't matter. So again, by central limit theorem, we know that the means are the same. So what I've done is, from previous section, I went ahead and drew this distribution. This is a sampling distribution of X bar. Right in here, the random variable again is X bar. For a 95.44% confidence interval, remember we said the Z is 2, so you go 2 deviation above, 2 deviation below. Now, what we would like to do now is we would like to generalize our confidence levels. We don't want always 95.44. What if we want it to be any number we like? Any number between 0 and 1, that means 0 to 100%. Now remember, with confidence levels, the higher the better. You don't want to be 60% sure that when you estimate something. You want to be almost for sure, almost 100%. So the more the better. Now, what I've done here is I've partitioned this normal distribution. Remember, for a normal probability distribution, the area under the curve, the entire area, so from negative infinity all the way up to positive infinity, this entire area is 1. So you can kind of draw inspiration from the distribution above. If you have 95% almost, that highlighted shaded region, 95%, that means outside of that interval, it's going to be about 2.5% on the upper tail, 2.5% on the lower tail, right? Just almost a little less than that. So what we've done here, because we're about to write a general formula, we're going to call this new symbol alpha here, which we've defined. Alpha is a number between 0 and 1. Okay, alpha is actually a probability between 0 and 1. So remember, the entire distribution has area 1. So inside of this interval is going to be 1 minus alpha, and by symmetry, half of alpha outside to the right, half of alpha outside on the left side. And what I have done is I have again generalized what you see up here with the numbers. -2 and 2 turns out to be Z alpha over 2 and Z alpha over 2 here. For the positive side, you go plus. On the negative side, the left side, you go negative. And here's the Z scale, just like we had up here. This is the Z axis. 0 at the middle, and Z sub alpha over 2 to the right, Z sub alpha over 2 on the left side. And inside this region is going to be 1 minus alpha. Okay, so this is the actual confidence. Oops, sorry, I didn't mean to do this one. And I just want to highlight it. And there we go. So this highlighted region, what I'm doing right now here, this region is going to be 1 minus alpha, which up above is about 95%. Okay, so there you have it. This is 1 minus alpha. Now, as far as the formula goes, so the 1 minus alpha times 100% confidence interval for mu of x is given by this formula now. X bar plus or minus z alpha over 2 times sigma over root n. Now this z sub alpha over 2, remember in chapter 6, I believe it was like section 6.1, 6.2, 6.1 I believe. We talked about a z sub alpha, and I mentioned that we're going to look at this later on in chapters 8, 9 and beyond. So that's what that z sub alpha over 2 is. Now, what is alpha here exactly? This alpha in this chapter, I like to call it the uncertainty level. Okay, that's what this is, the uncertainty level that is associated with our confidence level, or confidence interval, I should say. It is the uncertainty level. That's what that is. Okay. Oops, I don't know what I did. I didn't want to do that. But I do want to keep that uncertainty level intact. So let me just rewrite it. Uncertainty level. That's what that is. Sorry about that. Associated with the confidence interval. Now, the sigma x bar is what I used up here, right? Remember when we look at 95.44, we looked at sigma x bar, and there you go. So that's what the formula is, and here is what's actually in the book. This is what the book shows. This is often known as the one mean, means one population, z confidence interval or interval procedure. Our assumptions are important here, folks. You gotta have a simple random sample. If we don't have a simple random sample, the formula for computation of sigma over root n will be different. Okay. Second is that we have a normal population we sample from, or large samples. Remember, the large sample for us meant n must be at least 30, correct? So that's what that is. It means n must be greater than or equal to 30. That's the large sample. Doesn't sound that large. It's large in the eyes of central limit theorem. And of course here sigma must be known. That's very important. If sigma is unknown, we get into our next section in section 8.4. We'll deal with that. And here's a formula that I gave you. Our confidence interval runs from here to here. And that's precisely what I have written up here, x plus or minus. I like plus minus. It just shrinks the formula a little bit. And z sub alpha over 2, I'll show you how that is done. So there you have it, the formula. We'll look at an exercise in a moment. And StatCrunch, by the way, can do this for us. So just want to note something here for you. Again, this z sub alpha over 2 business on page 269, section 6.2. There you go. I knew I had that somewhere. We did an exercise number 79, and in there we talked about z sub alpha. Okay, so the difference now is you have half of alpha. Now, the 1 minus alpha 100% confidence level. So the typical confidence levels, I have listed them for you. They're 80, 90, 95, 99%. And the middle column gives you alpha over 2. Remember, alpha is the other side, the other part of this. If your confidence level is 80%, then that means your uncertainty level is 20%. Well, half of 20 would be 10. If you're 90% confident here, that means you're 10% inconfident, which means uncertain. Half of 10% would be 5%. For 95%, 5% uncertainty means 2.5% when you divide that by 2. Okay, and so on. Now the z sub alpha over 2 from that table, which is the exercise, I should say, that we did earlier, we saw these numbers. 1.2825, 1.645, 1.96, and 2.576. Now, we're almost nearing the end here before we look at an exercise. Here I have a list of factors that affect the length of the confidence interval. So the part that's plus or minus is what actually creates the interval for us. Okay, x bar, by the way, is your point estimate here. You see that? So the beauty of a confidence interval is this. It has the point estimate in it, plus or minus the number, which later on we'll see in the next section. We call that margin of error. And in fact, that's the advantage of a confidence interval over the point estimate. With point estimates, we cannot assess the error in our estimate. So for example, if I say the average rent in 92111 zip code is $1,200 for one bedroom, it's pretty much a hit or miss. Either that true average is $1,200 or it's not. And that's what the point estimate is. Now the drawback of a point estimate is when I say the average rent is $1,200 and you ask me, well, how certain you are? Well, I'm not that certain. I don't know. I cannot tell you my certainty level. And I cannot tell you how much error is in that number, which isn't a good thing, not being able to establish or assess the error. With confidence intervals, we can actually determine how much error is in our point estimate. So we'll do that in the next section. So confidence intervals have the best of both worlds. They have not only a point estimate in them, namely x bar here, but they also give you the amount of error in that estimation. So what factors affect the length of the confidence interval? I list them for you. The factors that affect it are what's in the box here, highlighted box. The z-score affects it, sigma affects it, and so does the sample size, right? Z affects it, sigma affects it, and sample size, of course, square root of it. So what I'm doing next is I'm looking at all three of these, the effect of each of them. What happens, for example, when sigma increases? Well, as sigma increases, so does this fraction. You multiply by z-score, so the whole right side gets bigger. Okay, so as sigma increases, so does the length of the confidence interval. That's what the up arrow means. Sigma goes up, the length increases. Sigma goes down, length decreases. Now I have highlighted it in yellow. This is what we would like. So we like to reduce the variability in scores as much as we can. This will lead into a narrower confidence interval, which is good. What about the effect of the sample size? Well, as the sample size increases, because of that reciprocal relationship, you see n is in the denominator. The bigger the n, bigger, bigger, bigger this is, the smaller the whole fraction gets, which leads into a smaller multiplier times z. So as n increases, the length actually decreases. That is a good thing. Okay, so the length decreases. Now what about the confidence level? Remember, that's when you go from, say, right up here, you go from 80 to 90 to 95 to 99. Well, as that happens, look at what happens to the z-scores. The z-scores get bigger, bigger, bigger. So that means we are pushing out into the tail of the distribution to occupy a bigger area, right in the middle. So the bigger z-score means, right in this formula, the bigger the z, the bigger the whole thing gets on the right side. So there you have it now, the effect of all of these. As the confidence level increases, so does the z-score, which in turn increases the length of your confidence interval. So the ones in highlight that I have here on this page are the actions you can choose in order to reduce the length of the confidence interval. Remember, we would like to have narrow confidence intervals. And finally, that's what I just wrote here. In general, we would like to have a narrower confidence band than the wider ones. So let's take a look at this example now. This is actually an exercise in your book. Exercise number 34. This is on page 336, okay, of your textbook, in case you want to find it in your book. Page 336. This one is actually an interesting exercise. This one reads, snakes deposit chemical trails as they travel through their habitats. These trails are often detected and recognized by lizards, which are potential prey. The ability to recognize their predator via tongue flicks can often mean life or death for lizards. And it goes on to and says the scientists actually observed 17 juvenile common lizards. Okay, so they observed 17 juvenile common lizards here. And they observed the response of these lizards to natural predator cues to determine whether behavior is learned or congenital. 17 juvenile common lizards were exposed to the chemical cues of the viper snake. The responses in number of tongue flicks per 20 minutes are presented in the following table. Remember, the tongue flicks per 20 minutes, that means each time they stick their tongue out of their mouth. That is a tongue flick. Every 20 minutes. So somebody must have observed these lizards for 20 minutes and actually counted how many times they stuck their tongue out and the tongue flicks. So here you go, for example, just to look at the numbers. This one lizard 425 times stuck his tongue out or her tongue out in 20-minute interval. This one lizard 510 and so on. The lowest number of tongue flicks is for this one. Only 276 tongue flicks. So this lizard is pretty relaxed still, I guess. It's not too worried about life. But then on the other hand, if I look at the high scores, who's got the highest score? There you go. Wow. Oh, no, actually 800. Can I do better than 800? No. 811 times per 20 minutes. Look at this one. More than twice as many times. This is a nervous lizard, huh? But then I would say this lizard is a survivor, right? But this one may be food pretty soon. This one with the lower tongue flicks. So anyway, these are just the numbers. They are what they are. Now, the question reads, find and interpret the 90% confidence interval. Notice, by the way, we don't have a 95.44 anymore. We have a standard 90, 95, 99 kind of numbers. 99% confidence interval. Now, in order to do this, looking at the formula, I need to find X bar, the average number of tongue flicks. X bar means I need to add up all the scores here and divide it by the number. So you can use your calculators if you want to. I actually went to StatCrunch and did it. Now let me show you how you do this in StatCrunch. This is exercise 34. I want to show you how I got the average. Okay, so I went to StatCrunch and this is exercise number 34. So let me scroll down to number 34. And here is the raw data. Okay, these are the tongue flicks. So to get the average, I went to Stat, Summary Stats for column. And left click once on flicks. And again, here I can just click on the mean, just get the mean. Compute, and that's all I really wanted. That's all I care for the formula. 532.17647 ... So that's where I got my number. So let me go back to note. And there you have it. I rounded the number from StatCrunch. Sigma is given. How did I know sigma? Right down here, the last line in the exercise reads, assume a population deviation of 190. And there it is. Now, next step, our confidence level, 90%. So 1 minus alpha 100% is 90%. That means alpha is 10%. Remember, alpha is the uncertainty level. In chapter 9, we're going to define alpha, a whole different creature. Okay? But it's going to be the same alpha that you're looking at in this chapter. And then we divide alpha by 2. We get 5% here. Half of 10% gives me 5%. And then the z of 05, again, is 1.645. These numbers will not change. The z-score will always be that for a 90% confidence interval. And then I went to the formula and plugged in for x bar. This is x bar, so I plugged in 532.18. Here's plus minus, plus minus. The z-score, remember the z-score is 1.645. That's this number here. Plugged in a sigma that was given, 190 divided by square root of 17. Then you reach for your calculators. The right side, you multiply 1.645 times 190 divided by square root of 17, and you get that 75.8. And now the plus minus, once you add another, you subtract 75.8 from 532.18, and that will give me this confidence interval that you're looking at. Okay, so this is actually the confidence interval that we're interested in. So how do we interpret this? I've written the interpretation in part B of that. I have it. He doesn't have part A, part B. I just put part B, the interpretation. We can say that we are 90% confident the mean number of tongue flicks per 20 minutes for all. Again, notice, folks, that's why I have it in red, and now I'm highlighting it. This is what makes it inferential. We are inferring to all juvenile common lizards. I don't know how many of those creatures there are. I'm sure there's quite a few of them out there. But the average number of tongue flicks, see, that's the mean here. The mean number of tongue flicks, that's what we're doing, is somewhere between 456.4 and 608. It's somewhere in that range. Now remember, we are only 90% confident. 10% chance. This is bogus. This interval is incorrect. But then we feel like 90%, the odds are in our favor that we have contained it, but nothing is guaranteed in statistics, right? Because it's based on sample. But anyhow, let me go down. Oh, looks like we're done with this one. So that wasn't bad, right? And hopefully you followed this one also again. And if not, please review the video and you can pick up the parts that you may have to review to make sure you understand everything. And I hope I explained everything as good as I could. I feel pretty good about this one. So with that, we are done with section 8.2. The next video would be about section 8.3, margin of error. So we'll take a break for now, and then we'll look at our next video in a few moments. Okay, thank you everyone. Okay, so let me show you now how to do the exercise that we just went through, number 34 in StatCrunch. So I have a StatCrunch up and running. I'm going to go to exercises from the book, chapter 8, and we're doing number 34. So let me scroll down to number 34, and here's the data for number 34. These are the number of tongue flicks per 20 minutes. Now, in order to do what we just did, that is confidence interval for one population mean, we're going to go to stat, right in here, stat. We're going to go to z stats, and we're going to go to one sample. Now here, because we have the data right in here, you see we have the raw scores. So I'm going to choose the option with data. Sometimes we don't have the data. They'll give us like the mean, the sample size, the deviation. Then we use the other option. That was the summary option. But for now, I'm going to choose the data. Click on flicks, and the standard deviation optional, because here we assume the deviation is known and it's given in the exercise to be 190. We actually want to type that number in. So we typed it in, 190, that's our sigma known. And let me go down here. So now down here we have an option of doing a hypothesis test or confidence interval. We do hypothesis test in chapter 9, so I'm just going to click on confidence interval, and our confidence interval was 90%. So you can type it as a decimal to be 0.9, and that's good enough. Hit compute, and there you go. We get exactly what we found it to be by hand, the numbers are exactly the same numbers. So as you can see, you can do this in StatCrunch, and that's how it's done. You can actually, your options are, for instance, you can here copy this, your output, and then it tells you how to paste it into such as Word document or something like that if you like. But for now, I just want to show you that you can do this in StatCrunch, and that's what this is. So hopefully that was easy to follow, working with StatCrunch to get the same numbers much easier and faster. And with that, we are truly now done with this section.